Hello everyone. We have a question which says that a particle P of mass 0.3 kg. So there is the particle P having a mass of 0.3 kg is held in equilibrium. So the condition is an equilibrium. Above the horizontal, the particle is held in equilibrium above the horizontal. That means this AB is representing the horizontal and this particle is held in equilibrium above the horizontal by a force of magnitude 5 Newton, and definitely it is held in equilibrium by the force of 5 Newton. Acting vertically upward, yes, we can see acting vertically upward. The particle is attached to two strings, and this particular particle P is attached to two strings PA and PB. Yes, we can see that PA and PB over here of length 0.9 meter and 1.2 meter respectively. The point A and B lies on the plane and angle APB is 90. Yes, we can see this point A and B line on this horizontal plane, and the angle APB, which is from here from A till P and B, it is representing a 90 degree. Written over here, find the tension in each of the strings. So basically we have to find the tension in both the string, this string and this string. They have not given us any angle, so definitely we have to find the angle. We have to know the components, the horizontal component as well as the vertical component. So just split up the diagram properly so that we could understand what the horizontal and vertical components are. Before splitting up into component, first of all find the angle. As you can see, this is a right angle triangle because 90 degrees over here, and this 0.9 meter and 1.2 meter is basically representing the length. If I draw it, so based on this 0.9 and 1.2, which is basically the length of the strings, so we could easily get the value of angle. For example, this is an angle theta. Let's suppose this is an angle theta that is being considered. So if this is an angle theta, so definitely the opposite side of 90 degrees hypotenuse, the side next to the angle is always adjacent, and the third side is always opposite. That means we have the adjacent, we have the opposite, and the relation is tan theta is equals to opposite over adjacent. That means 1.2, which is opposite, over adjacent, which is 0.9, and theta is equals to tan inverse of 1.2 divided by 0.9. That means we can say that yes, the angle is 53.1 degree. As you can see over here, this angle is 53.1. I have written over here 53.1. This is 90 degrees, so I can add this 90, this 53.1 over here, and after adding 53.1 and 90 and subtracting it from 180, we can have the third angle as 36.9 degree. Now we have both these angle, and now we could easily split them up into horizontal and vertical component. So this 0.9 meter and 1.2 meter was just given to us just to find the value of the angle and nothing else. Now this 0.9 and 1.2 meter has nothing to do with the calculations. It was just for finding the angle. In the question, they gave us the mass of the particle is 0.3 kg. It is a mass, so definitely just convert it into Newton, because we know that W is equals to mg, weight is equals to mass into gravity. So 0.3, which is kilogram, the mass of the particle multiplied by 10, 3 Newton, and definitely the weight is always downward, and you are applying a force of 5 Newton upward. According to the question, find the tension in each of the strings. So we have to find the tension in this string and this. Over here the point A, over here the point B. So I have written over here in this string the tension A, which is represented by TA because A is over here it is B, so the tension in this string is represented by TP. Now very simple, we have to split them up into horizontal and vertical component, but before that we have to understand what the horizontal and vertical components are. I have seen that most of the students have misconception that the horizontal component is always a cos component. No, it is not like that. If this is an angle theta given in the question, then the side next to that would be a cos component of that particular force, and the opposite would be a sine component of that particular force. But if the angle given over here is with vertical, then definitely the side next to that would be a cos component of that particular force, and the opposite would be a sine component of that particular force. So it is not like that the horizontal is always cos component. It depends upon the angle where the angle given is. So the condition given to us in the question was an equilibrium condition. So based on that equilibrium, we know that the opposite forces are equal, and when we say that the opposite forces are equal, that means the opposite horizontal forces are equal as well as the opposite vertical forces are equal. And when we say that the opposite horizontal forces are equal, so we would work out for both horizontal as well as vertical. If you just look at the horizontal forces, we can see that, and if we just look at the diagram, we can see that we have just one horizontal force over here and the other horizontal force over here. This horizontal force is making an angle of 53.1 and the force is TA. So this horizontal force would be TA cos 53.1. It is to the left, so TA cos 53.1. The other horizontal force is to the right, making an angle of 36.9 degree, and this force is TB. So this horizontal force would be TB cos 36.9, which is over here, because both are in opposite direction and the condition is an equilibrium, so we have made it equal. So after making it equal, we can create a condition for TA is equals to TB cos 36.9 divided by cos 53.1, and after dividing we have 1.332, and this is TB. So we have an equation in terms of TA and TB, because our target from the question, it says that find the tension in each of the strings. So our target is to get the value of this TA and TB. So this was the equation from the horizontal forces. We will create one more equation from the vertical forces. If we just look at the diagram, we can see that we have one force which is pointing upward, 5 Newton, and we have three forces which are pointing downward. One of the force is the opposite force of this TA. Angle is over here, so this would be TA. This arrow downward indicates the opposite force of this TA, and that would be TA sine 53.1, which I have written over here, TA sine 53.1. Similarly, this vertical force, this arrow I have made downward, is the vertical force for this particular TB, because the angle is over here. So this force pointing downward would be TB sine 36.9. I have written it over here. And we have one more force, which is the mass of the particle, and definitely we have converted it into Newton by multiplying by T, which is 3 Newton. So we have basically three forces: the vertical force of this TA, the vertical force of TB, and the weight of the particle. So if we add all three, which is TA sine 53.1, TB sine 36.9, and plus 3, which is this one, if we add them up, it would be equal to 5, because 5 is pointing upward. Why? Because of the equilibrium condition that the opposite forces are equal. So three forces downward, one force upward, so the sum of these three would be equal to 5, and we have made a condition, and instead of this sine 53.1 we have written 0.8 of TA. Sine 36.9 is 0.6 for TB, equal to, and this 5, and when this plus 3 moved on the other side, 5 minus 3 is 2, and we have equation 2. Our target is to find the value of TA and TB, which are the tensions in both the string. So we have two equations, equation 1, equation 2. We could simply substitute the value of this TA in equation 2. So 0.8 over here, and over here it is TA, and instead of TA we will write 1.332 TB. So instead of TA we have written 1.332 TB plus, and this 0.6 TB is equal to 2, as you can see. Now the complete equation is in terms of TB. Simplify it and get the value of TB, which is 1.2 Newton. After getting the value of this 1.2 Newton, just place this value of TB in the first equation, which is TA equal 1.332 TB. Just place the value of that over here, and this TB is 1.2 Newton over here, and TA is equals to 1.332 multiplied by TB, which is 1.2, getting the answer of TA, which is 1.6 Newton. So finally we have found the values of TA and TB, which are basically the tensions in both the string.